and the session starts with a discussion led by Feng Kun Guo from Beijing and Tomasz Skwarnicki from Syracuse. And we are starting.
So we have 20 minutes to do introduction. We have decided with Feng Kun to split it into 10 minutes for each. I will lead with experimental overview, and then Feng Kun will take it more into theoretical grounds and take it to the discussion.
Please.
All right, so let me share my screen. Can you see it?
Yes.
All right, so we selected to talk about heavy flavor exotic hadrons. This is, I may be the only true experimentalist here, so I will give you selected highlights of this topic. Now this is very broad, so I cannot talk about everything. I just selected some most interesting signals that have been seen. Now, if you think about status of our understanding of Hydron Spectroscopy right now, it's really very poor. We know that the lightest hadrons in each quark configurations are predominantly just bound states of either QQ bar or QQQ, but a lot of things motivated by QCD is not settled. We don't know if diquarks are good building blocks for more complex quark structures like tetraquarks and pentaquarks. We are not even sure about full role of diquarks in baryons. And it's still not experimentally settled if gluon can be among dominant hadron constituents, either in glue balls or hybrid mesons or baryons. We know that nucleons bind together via residual strong force, but we are not really sure if mesons have similar nuclear type bindings either to other mesons or to baryons. These are often called molecular states. So if I think about this, this is pretty scandalous situation given how long we have had exact theory of strong interactions. And the reasons are both theoretical and experimental in nature. Theoretically, it's just very difficult to simulate on lattice full dynamics of multi-quark states or unstable states. On the experimental side, there are a lot of limitations too. For example, producing one of the most interesting quark configurations with 2 big quarks and 2 light quarks will be very difficult, both because of production of such states and then the reconstruction. Now, why did we choose to focus on heavy hadrons? Everybody knows about J-psi revolution, right? That essentially put quark model on solid grounds. The whole family of very narrow states with electromagnetic and soft hadron transitions between them. Mass spectrum clearly fitting non-relativistic quark model. So since then, we have been preaching in textbooks with mesons are simple and correspond to various radial orbital momentum and spin excitations of QQ bar. Now, once you reach open flavor thresholds for decay to two mesons with each with one heavy quark, the excited states were expected to decay to one of these combinations depending on the quantum numbers and be generally broad. Now, there has been a second charmonium revolution happening since discovery of X3872 in 2003. Since then, we detected many more oddly behaving states than what was expected from simple model. They have, in general, very large transition rates to the narrow charmonia states. So by now we know that once you reach that open flavor threshold, situation is complicated, and we haven't really fully understood all the effects which are happening here. This also makes you wonder about our understanding of light hadron spectroscopy, since such flavor thresholds are essentially, immediately after one or two the lowest states you reach such thresholds. So I'm going to just mention a few most spectacular experimental signals. It all started from X3872, discovered by Bell in decay to pi plus pi minus J psi. The system was produced in D decays, which provided for very clean spectrum. You see here, this big peak is the last pure charmonium state, psi 2s, and then unexpectedly a very narrow peak was observed at DD star bar threshold. By now, thanks to recent LHCb work, we know that if interpreted as Breit-Wigner, the width is only around 1 MeV. This state could be just an excited P state, which was expected in this mass range. It would be narrow because it cannot decay with these quantum numbers. It cannot decay to DD bar. So if it sits right at the threshold, it would be narrow. It would be somewhat surprising. It would sit right at the threshold. Therefore, this suggests that maybe that state is actually has something to do with this loose type of binding between D0 and D star 0 bar. So maybe it's a molecular state. Some people are proposing also compact tetraquark like diquarkonium. However, in these models, not only mass is coincidence, but it's also difficult to come up with natural explanation for such extremely narrow width.
Tomasz, a reminder, you have 3 minutes.
All right, let me hurry up then. Now, we know this is not a normal pure charmonium state because it violates the discovery mode. It violates isospin. Let me advertise recent work I have done with my student who just graduated. We are trying to publish this, but it was shown at Lepton Photon. LHCb has now enough data to do proper analysis of dipion mass spectrum. So we resolved rho contribution, which is isospin violating, and omega contribution, which is isospin conserving. And from this first time properly, we extracted the ratio of these coupling constants, and they are a factor of 10 bigger than what expected for normal charmonium state. So we know this is not a normal charmonium state. There have been other spectacular peaks observed at meson thresholds, namely C sub B and C sub C states by both Bell and Bess. They are narrow. Masses peak slightly above thresholds, but proper coupled channel analysis, at least for one of them, shows that the V-pole is slightly below threshold. So this could be molecular states as well. There's the most striking experimental results for narrow states at the thresholds came from actually pentaquark channel, late CB study of J-psi proton system produced from lambda B decays. 3 narrow states were observed right below sigma sub C, D or D star thresholds. A number of narrow states agrees with expectations from molecular model.
Tomasz, a reminder, you are now 10.5 minutes.
Okay, I will speed up. There are some other less significant observations of threshold states. So there are plenty of them. They are not necessarily all of the same origin. One thing for sure, that in the future we'll find more threshold states. There are also a lot of broad states that are exotic in nature. Since I don't have much time, I will not go into it. So we know that there is more than just threshold states which are going on in this mass region. Some really interesting signals were observed in a couple of last years. J-psi structure observed by LHCb in 2020. It could be tightly bound tetraquark, but the structure is in the region where coupled channel effects for J-psi psi prime and psi double prime could play a role in shaping the mass structure. Now, LHCb discovered doubly charmed baryon in 2007, and Marek and John correctly predicted its mass, and after that they used the same model by substituting this quark by anti-diquark. They should behave same way, right? And predicted, made these predictions for masses of lattice 1+ states with different combinations of heavy quarks. And the excitement was that BB U-bar D-bar state would be clearly long-lived, would have no strong decays. This was discussed in detail by Atsushi yesterday. Now, what I never told Marek is that once he presented this plot, I took it to our smartest postdoc at Syracuse, Ivan Polyakov, and told him I knew that this was hopeless to present data, but I suggested looking for doubly charmed state. It took him 4 years, but he was a very talented guy and found out how to do it experimentally. And last summer, we published the results on this spectacular and narrow state decaying to D0, D0 pi plus. which could be from Atsushi's talk, either loosely bound molecule or a tightly bound diquark state. My prejudice is for later because it was observed in direct production, in prompt production. That seems to be true for compact states. Unfortunately, detecting BB state which can distinguish these two types will be extremely difficult. All right, so let me now, sorry for taking longer. Now, Feng Kun, this is now in your hands.
Okay, thank you. Thanks. Thanks, Tom.
Thank you, Tomasz.
So now let me start sharing. And first, thanks to Marek for the invitation. So let me just continue with some theoretical understanding of what Tomasz already talked about. So I will actually focus on in the introduction part these mostly on the near threshold structures. So here just to recapture the essentials in Tomasz' talk. So basically this is the list of all the structures observed in the past and in the recent years. And there are a few milestones, as Tomasz already talked, the observation of XA72 by Bell, and then followed by the observation of charged charmonium or bothmonium-like states, the ZB states, and also ZC states, and then the PC and TCC we just heard about. And many of them are really close to thresholds of a pair of open charm hadrons, and their observation really promotes lots of theoretical studies on trying to understand their internal structures. So basically, so we know that's basically in the quark model notation, we have this conventional hadrons and this exotic hadrons. And then this exotic hadrons, we talk about this something like the compact tetraquark and also pentaquark states. And there is something similar to them, but it's really analog of the nuclei, which would be bound states of 2 or more hadrons by residual strong interaction force. We call that hadronic molecules. So let me just make connection to flux tubes and confinement. And then this would probably we can learn some hints about the confinement or the flux tube formation from studying this spectrum, because many of them were supposed to be hadronic molecules, and they might also be compact tetraquark states. But these two guys would have different flux tube configurations or topologies. If this is a hadronic molecule, that would be corresponds to just flux tubes just within a given hadron, and then these two hadrons they interact through the exchange of mesons, for instance, phenomenologically speaking. And then if this is the so-called tetraquark stuff, would be the heavy quark and heavy antiquark, or the quark and antiquark, they are a bit far away from each other, and then the flux tube formation would be something like this. Actually, there have been some lattice calculations or lattice simulations of this color.
Bien, ¿cómo le va, Elsie? Sí, todo muy bien, gracias a Dios.
Not a question to me, okay? So let me just continue. So this, there have been lattice calculations on these color electric field distributions inside multi-quark structures. For instance, this paper by Okiharu et al. They studied the 2 heavy quarks and 2 heavy antiquarks, the static color sources. And then what they found is that if the distance between quark and antiquark is large, and then the potential would be like the configuration is showing this way. So it's like this 2 Y-type junctions and then connected to each other. If the distance between the quark and anti-quark is very small, and then this would mean the color configuration actually looks like a 2 meson type. So this is like this one. So let me now focus on the near threshold structures, and I will tell you my understanding of why there should be many near threshold structures, in particular in the heavy flavor sector. So basically, we can consider some T matrix for a couple channel system. For instance, we can consider the 2-channel system, one channel with a lower threshold, which I call channel 1, or the channel with higher threshold, I will call that as channel 2. So basically, in the energy region around the threshold of channel 2, we can write the T matrix using unitarity. We can parameterize this T matrix in terms of this form. This contains the 3 parameters, which I just write that as A11, A12, A22. These are 3 real parameters. And then the only really non-singular, well, the non-regular part, the part that has a singularity in this amplitude is just given by this square root function. This is basically the center mass momentum of particles in channel 2. Now I want to focus on the region around channel 2 threshold. And we will see this determinant of this inverse of T matrix. This develops a pole. This has this kind of form. So basically, this A22 effective looks like a scattering length of the channel 2, but now it is a complex number because it receives contribution from lower channel, which is channel 1. But unitarity tells us that the imaginary part of this is scattering length, effective scattering length is negative semi-definite. So the inverse of this is scattering length. And then this just tells us that the behavior of the line shape or the amplitude around this threshold of channel 2 can be really determined by the sign of this inverse of the real part of the scattering length. So basically, if the interaction is attractive, so this means if we have the positive real part of this effective scattering length, we will have something like this. So this we will always have maximum exactly at the threshold for the absolute value of this T matrix T21, and then this decreases when the energy is far from this threshold of channel 2.
Feng Kun, just a reminder, we have 7 minutes. We are past 7 minutes now.
Okay, thank you. So the width of this narrow peak actually is anti-proportional to the reduced mass of the particles, and then if this guy is negative, and then actually the maximum value is at some place below threshold. And if A22 effective is very large, this means actually the pole is close to threshold. This would correspond to either bound state pole or vertical state pole if we neglect the imaginary part. So, but the same pole structure actually can behave very differently in different reactions. For instance, different from the previous one, one can think of some reaction dominated by this T matrix element. And then this guy has a 0 in the numerator. And then if the interaction in channel 2 is very strongly attractive, and then this 0 can produce a dip in the line shape. So although all these lines have the same pole structures, correspond to thresholds with the same pole structures, but they behave very different from the previous page. And this kind of stuff has been seen in data. For instance, this dipside case into 5 pi pi omega 5 pi. In pi pi environmental distributions, the same pole, the F0 980, this behaves really differently in different reactions. And there's another possibility for enhancing near threshold structures, which is the so-called triangle singularity, which is the leading law of singularity of triangle diagram. And this can be close to the physical region when this kind of configuration happens. This basically means if you consider decay of A particle into B and R, and then this B and R can both go on shell, and this R particle decays further into C and D, and then all of R, B, C, they move collinearly or anti-collinearly. So this C and B, they move in the same direction. And if C moves faster than B, and then all the vertices of this triangle diagram would happen like classical processes. In that case, we will have triangle singularity close to a physical region. And then this corresponds to the mass of this R in this side. So it's just it can interfere with the lattice plot boundary at this point, and then this point when we project onto some environment distribution produces a peak. This is a logarithmic singularity. So sometimes this produces signals mimicking resonance, or it can also enhance production of near threshold resonance. So let me just.
We are past 10.5 minutes now.
Okay, so I'm closing with this pitch. So now you see I just show you the sensitivity of this triangle singularity to the energy. So basically you can see the shape of a triangle singularity. So this basically is like this guy. So it looks like a resonance, but this looks like resonance in both directions of different kinetical variables. Now here it comes to the questions for our discussion. So the time for the introduction is over. I just leave this page to you to see what we can discuss in the following time. And of course, you can also raise up your questions. Thanks.
Is that it, Feng Kun?
Yes, yes, yes.
Okay, thank you very much. So we now open for discussion. And please raise your hand or virtually pressing on the appropriate button on Zoom, or just open your microphone and that. Okay, so we already have some people who want to talk. I see Atsushi, I see Arkady, I see Kobe. So Atsushi, please.
Okay, thank you. Nice to meet you, Feng Kun. Hello.
Hi.
I want to ask about the threshold CAS and the triangle anomalies. And I think for the two-body threshold CAS, if this line, well, the shape of the cusp, it probably depends on the kind of the interaction. What I mean is that suppose there is no interaction between the two particles in this channel, the cusp is relatively weak and not very easy to observe, probably by experiment. So you need some interaction to really make this enhanced, like a structure for the cusp. But for the triangle singularities, do you still need this sort of interaction dependence on the, well, for the line shape, whether this really sharp, easier to observe or not? This is a question. Can you?
Yeah, thank you. Thank you, Atsushi. So this is a very good question. Indeed, as you mentioned, the shape of this cusp really depends on the interaction. Actually, here we can see the width of this this kind of. Let's just focus on this the structure really, which peaks exactly at the threshold, and then the width of this kind of peak is anti-proportional to the reduced mass, and and also it is anti-proportional to the scattering length squared. So basically, when you have stronger interaction, and you will have a sharper peak. of course it must be attraction. Okay? Yeah, indeed, this is really determined by the interaction strength and also the interaction sign. And for the triangle stuff, and the location of this singularity actually is purely kinematical. This is really just determined by these kinetical variables, the masses and the involved energies. But the strength of this peak indeed is proportional to, for instance, to this coupling, the coupling of this interaction at this interaction vertex. So when you have stronger interaction, you can have more prominent peak. So that's it.
Okay. Thank you very much for this clarification.
Thank you. And the next comment or question is from Arkady Weinstein.
Hello, everybody. I wonder, in this couple channel case, or just, when you have this example where you have this 1/, scattering length, small quantity, right? Then it is characteristic dependence on as you describe, from momenta K there, which is not the same as normal Bragg-Wigner, right? So it's a different one. Moreover, it could be so-called virtual state or whatever, where this 1/, scattering length is the opposite sign. So it's not in this way, not attraction, but say repulsion. Still, this characteristic dependence on, I think this cross section is becoming large, but like 1/K, it is still there, right? So I wonder to what, maybe it's more experimental question, but still, I wonder to what extent, these details, this particular behavior in for those states, which is 1/K, could be distinguished from Bragg-Wigner in experimental data. So maybe it's for Tomasz. I'm not sure who is better positioned to answer this.
Yeah, so it definitely, you have to take it state by state, right?
Yeah.
In terms of experimental situation. So for example, for X3872, enough data, we have enough data in pi plus pi minus J psi channel mostly that the V-line shape has been studied. There's a paper published, I believe, last year. And different models have been tried. And there is some indication that it's a true resonance rather than a virtual state. However, coupled channel analysis at this point is missing. We know that V tail of this state, which sits right at the threshold, can decay to DD star bar. So this was a single channel analysis so far, but I'm hopeful in this case that we will be able to do more sophisticated coupled channel analysis in the future.
But in case of this, what's called TCC, this double charm example, was it possible to do this type of, you see, because
yes, you will in the paper you will find the analysis which with both naive approach, but also non-Bragg-Wigner parameterizations. There will be more data in this case. I'm not sure that the coupled channels are relevant in this case. So this may be a simpler case, but in all these situations, unfortunately, when these things get very narrow, the experimental resolution is an obstacle to sensitivity, right?
Yeah,
because
but it's also,
even though our resolution is very good, of the order of couple of MeV. Or in case of T sub CC, it's less because
yeah, but it's also there is a phenomenon of instability of, say, DD star, for example, which also would mix up with this, right?
Yes, I mean, yes, it can get complicated, and certainly involvement of theorists to try all the possible parametrizations is welcome.
Okay, thank you.
I mean,
So,
the data is
any
published, so you can get the data from websites, and you can also get experimental resolution from the paper.
Feng Kun, do you have any comments on Arkadi's question?
Yes, I want to add a few sentences. So basically, yes, indeed, this is a very good point. Indeed, there are cases that can be vertices. Vertices actually means this scattering length, the absolute value of the scattering is very large, but it still has the sign of attracting interaction. When this vertice becomes bound state, and then it switches sign to just like a repulsive interaction sign, but it's still attractive interaction, but with very large scattering length. And vertical state and bound state, if they are really close to threshold, and then they are hard to be, it's not easy to be distinguished from each other. But actually, you can see from this plot, all of this, the blue line and the red lines, this would correspond to the amplitude having vertical state pole. So this is exactly S threshold. But this you see this kind of line shape is asymmetric. So this is not symmetric. And also, if the bound state pole is also close to threshold, you will see something like this green line. So the peaking position would be below threshold. So if the bound state is really close to threshold, and then it's not easy to distinguish. If this is a bit far away, and then in principle, if the energy resolution is good enough, one could distinguish them. And also in some realistic analysis, these couple channel effects are taken into account. And then in that case, one could fit to this data by extracting the T matrix parameters and set for the pole to see what the pole or on which Riemann shapes the pole is really located.
Thank you. We have to move on. Kobe, please.
Yeah, I want to make a comment and ask a question. The comment is about this distinguishing between a molecule and a genuine exotic tetraquark. I believe that there is a simple criteria that one can use. So suppose that the system is of the form of a diquark and anti-diquark with a string or a flux tube in between. Then this string has to have a Regia trajectory of excitation. So one can measure the excitations of this state, and if it has a structure of this Regia trajectory, then it will be a clear-cut indication that it is a genuine and not a molecule. Now, the other condition or the other criteria is that if it's a highly excited state and it's above the threshold of decaying into a baryon-antibaryon, then clearly it is a genuine exotic tetraquark. And there is, I believe, such a case of a state of 4660, which decays predominantly to lambda c bar, which I think is a clearly indication that it is a genuine tetraquark. Now, the question that I have is to Tomasz, and indeed the question is related to what extent are experimentalists looking for channels which are decaying into baryon-antibaryon, because that will be a smoking gun of such a tetraquark structure.
Well, I mean, we can look for them, but it's a matter of sensitivity, right? So, and again, whether we would already have sensitivity to such decays, it's a case-by-case basis, right? Which exactly baryons are you talking about? Now, in general, LHCb, which is leading many of these measurements nowadays, is very good in detecting all charged final states, but you know, branching ratios to channels with very few charge tracks matter, because if you ask for too many charge tracks, your efficiency goes significantly down. So in general, we are restricted to simple final states. So again, the question is, what is the branching ratio? And what type of baryon are we talking about?
Well, I think even an example, I mean, you mentioned this resonance at 6.9 GeV, which believed to be C bar C bar. And there is another bump, which is at 7.2 GeV, which is above the threshold of decaying into a cascade CC bar. So if it can be indeed detected that there is this channel of decaying into baryon-antibaryon of cascade CC, then I think it will be clear indication that it's indeed a Tesla quark.
Well, it's an interesting point. You know, offhand, my guess would be that right now we don't have enough sensitivity, because we barely detected these effects in the easiest channels, right? So potentially detecting such channels in the future. LHCb has two upgrades, one going on right now and another one in maybe a decade from now. So there will be substantial increases in luminosity. So offhand, we are not sensitive yet, but possibly we could be sensitive in the future.
Okay, thank you.
Thank you very much. Now, the next question or comment was from Giancarlo.
So,
Yes,
excuse me. May I just?
Yes, thank you.
I'm sorry.
Sure. Excuse me, Giancarlo. Feng Kun has a comment.
Yeah, so I just want to mention this because Kavli just mentioned this Y4660, Y46, and he mentioned that this could decay into to lambda bar as the main decay mode. Actually, there are new data. I think what he mentioned is the data from Bell some years ago, and there are new data which are from BESS3. The BESS3 data, of course, they did not go that far up to 4.66 GeV, but they have data from lambda bar threshold up to a few tens MeV above threshold. And they have reported several data points, and basically all these data points are really flat. So up to the energy point that they reported, there is no trend of increasing further. So there is a kind of tension between the new. Actually, the BESS3 data are really with very high precision with the old Bell data. So they are the BESS3. I think they will publish data in larger energy range in the near future. But so far, they has only data up to around 4.6 something, but not that high enough.
Thanks very much. This is very interesting. Thanks, Feng Kun. And Giancarlo, please.
Yeah, thank you. I have much appreciated the previous two talks and the presentation that they made. I have perhaps just to understand, to see if I have understood the Feng message. So you are telling us that triangular singularities can produce narrow peaks that could mimic narrow resonances with the mass near to two meson thresholds, perhaps with an asymmetric shape of the peak. Is that the message?
This is one of the messages. Yes. Sometimes this kind of mechanism can really produce peak mimicking a resonance, and then but this kind of phenomena should be there, and then one should really analyze carefully whether the signal is really due to this kind of mechanism, or that's due to genuine resonances. So there's would be a warning message. Not all of these structures reported
of course
really corresponding to genuine resonances. But for instance, in the case of the ZC3900, there have been some analysis taking into account this kind of mechanism, and so far different groups have not really reached to a consensus. But the very key point is that this kind of mechanism is really sensitive to energy. So as long as the experimental group publish data with more energy points, and one can see whether, for instance, the ZC is really, one can make final conclusion with the ZC really corresponds to a real resonance, or does it produce it by this kind of effect. Actually, I'm in favor that ZC really corresponds to some resonance from our previous analysis.
Okay, thank you.
Thank you, Feng Kun. And now Igor has a comment or question.
Yeah, thank you. Yeah, I was just wondering about if someone could comment on the role of Heyer's the heavy quark symmetry, because it looks like there are two types of states at nearly the same mass. One is this X3872, and the other one is TCC at 3875. So I was wondering if for, say, BB and BB bar, you expect there may be even better relation. And another question is, so I guess the confusion so far is that if you look at the estimates of the tetraquark mass, the compact object, they also come out very near threshold, but for charm, but for BB, they seem to come out way below threshold. Is there any reason to doubt the existence of such state, and whether for the BB system there actually could be two separate states, one very tightly bound and the other one near the threshold for BB star? Basically, these two questions.
Feng Kun, you want to answer?
Yes, yeah. As for the first one, so first one you asked about the whether one would observe the bottom analogs of the XA72 and TCC, right? So whether one can use heavy quark flavor symmetry to relate this the charm stuff to the bottom stuff. I think yes. For the interaction, for the potential, the interaction between the charm and anti-charm, indeed we can use heavy quark flavor symmetry to really relate the for instance the interaction between D and D star mesons with the B and B star mesons. But there is one subtlety, which is that this kind of systems are all non-perturbative, so the masses also come into play a role through the Schrödinger equation, for instance. And for instance, in some calculations, assuming the heavy quark flavor symmetry for the heavy meson interaction, and that can produce the XA72 as a D star bound state close to threshold. The same model, the same calculation would produce a B star or B bar B star bound state, which would be a few tens MeV below threshold, because the bottom meson is heavier, so it's easier to be bound. So the body energy is larger, and then would be, for that kind of system, would be very difficult to be detected. Why this XA72 is easier to be detected? Because this is really close to D0 star threshold, and also this this gives it the ability to decay easily through acid spin breaking, as Tomasz just talked. But for the BB star stuff, this is much below the BB star threshold, and then the acid spin breaking possibility is much less, and then the ozone pi would not be a preferred decay channel for that stuff, and then that's not easy to be observed. As for BB star, I think if the TCC is also kind of a molecule stuff, and then one would also expect BB star, which would also be bound by tens of MeV. But I think there should have been some model calculation about that. Yeah. As for the second question, second, you asked that the BB stuff, this is much deeply bound, for instance, for the BB doubly bottom tetraquark. Yes, I think indeed in that case, as the predicted, for instance, by Marek, this is bound about 200 MeV, right? If I remember correctly.
Yes.
And then that would be different from, for instance, the molecular prediction, which would be a few tens of MeV.
Thank you.
Could there be two separate states there, then one molecular and one tightly bound?
Could very well be, Igor. It could very well be. If it turns out that TCC has a major molecular component, then you probably expect two states in the B sector. One would be a deeply bound compact tetraquark, and the other would be well bound, but not as deeply molecular state.
And they were mixed with each other, right? To shift also.
In this case, they probably won't mix too much, right? Because their masses are quite far.
There will be, there could be, 100 MeV apart.
Yes.
So mixing would be suppressed. We have to speed up.
Okay, thank you. Thanks a lot.
Thank you. We have to speed up because we are fast approaching the time limit. So Guy de Teramon, please.
Yes, thank you, Marek. Well, I have seen that there is two models or two configurations which have been discussed in the conference, and mostly compact state, like compact tetraquarks, and hadronic molecules. But this is fine for the hadronic molecule, just as an example, a BB bar, because you have a common quarks which can be exchanged. However, if you have, for example, CC bar and QQ, then to first order, you do not have a quark exchange. And that left Voloshin, I recall one of his last papers, and he's very clear in the hydrocharmonian picture, where you have two gluons or Pomeron, whatever. So I wonder why this has not been mentioned in the conference. Probably, I imagine that the J over psi photoproduction have shown that this mechanism gives a smaller contribution. However, it's important in the sense that it can give some hints into the origin of the proton mass, for example, using the conformal anomaly and this type of things. So I just asking why you have not discussed much about the hydrocharmonian picture configuration.
Maybe Feng Kun wants to answer.
Yes, yeah, indeed. There is this hydrocharmonium picture proposed by Misha Voloshin some more than 10 years ago. Indeed, that would be a picture that the system could be formed by the interaction between charmonium and light hadrons. And actually, I have some backup slide which I show here. That's basically interaction between two dipsi, which is have similar interaction as hydrocharmonia when we see. There will be the interaction between two states, for which the exchange of mesons or quarks are really suppressed, and then they would interact really mainly by the exchange of soft gluons. And then that kind of stuff, one could also think of as the hadronic level, exchange of 2 pions or kaons or even more. And indeed, one could study that case, and even this kind of stuff could indeed be strong enough to produce state not far from threshold. Indeed, I've seen the hydrocharmonium picture. Well, that kind of instruction is also not really negligible. And yeah, I just didn't really have time to cover all of these things.
Well, I just have a quick comment about this. You know,
Yes.
for states like X3872 or Z sub B or Z sub C, which are very close to the 2 meson threshold, it would require an extraordinary coincidence for them to be to have a significant hadrocharmonium component or bottom hadro-bottom component, because just the masses coincide and the decay rates into 2 mesons are huge. So this, I think, makes it unlikely. For tetraquarks of the other kind, which contain 2 heavy quarks rather than a heavy quark and an anti-quark, you don't have the analog of charmonium because they cannot exist as a separate meson. We have to move on, and Andres Milga, please.
Okay, so I just want to recall one of my old papers. Back in '86, Alla Badalyan, Boris Yov, and me, well, made an estimate for tetraquark, compact tetraquark system made of C quarks. And our estimate was the lowest state was sugar scalar, and the mass was 6.5 GeV, and the vector state 1 minus had the estimated mass 6.75 GeV. And so we just solved Schrödinger equation. So we took pairwise quark potential and applied the same methods as people do for nuclei. So it's hyperspherical harmonic, something like that. And so that was our estimate. The estimate for the total width, the state is still above threshold, so it can decay, for example, a vector state in Jep psi and high. And so the estimate for the total width was 10 MeV. And as far as I understand, modern estimates are different from ours. But so I think it makes sense to look again and compare the technique, theoretical technique, which led to this estimate. So that's what I wanted to say.
Andre, you're talking about the 1987 paper in nuclear physics.
Yes, yes.
I just saw it. So did you also address, I wasn't aware of this, but did you address the bottom quarks also?
No, no.
Because there have been some conflicting reports from CMS mostly that they see something interesting in 2 upsilon channel and so on.
We made estimates for C quarks, and then we also applied that for CC bar, SS bar. It's less reliable because for light quarks, well, it's a little bit less reliable, we think. But we made this estimate, and the mass was 4.8 GeV for this system.
Okay, very interesting. Thank you.
Okay.
Now, I have a quick question to Feng Kun. Can you show again, please, the diagram showing the flux tubes for the various distances? Yeah, so the point I wanted to make is that the distance between this is the case where you have a heavy quark and a heavy antiquark.
That's right.
But so the distance between the heavy quark and the heavy antiquark in these lattice simulations is dialed by hand, but in the real world, it's something that is determined dynamically, right? I mean, the system determines the distance.
Yes, definitely.
And moreover, something very interesting happens, I think, which is very relevant to this workshop. If you have two heavy quarks rather than a heavy quark and an anti-quark, they get very close to each other, especially two big quarks, so close dynamically that probably there is no flux tube. They get into a Coulomb regime. So when you have a tetraquark, a compact tetraquark, which consists of two big quarks and two light antiquarks, on the heavy quark side, there probably is no flux tube between, I mean, there is no junction. They just act as one color anti-triplet source. But on the other side, on the side of the light quarks, most likely there is going to be a junction. So this thing, in terms of flux tubes, looks very much like an antibaryon with one very heavy quark, which is twice the mass of the bottom quark, and two light antiquarks. So this is going to be very interesting. Maybe people can do it on the lattice. And I think it's relevant for our workshop because through careful measurement of the mass and other properties of such an object, we may have a grip on the flux tubes, at least in this case. All right, I think we have to stop here because there is a break of 20 minutes. And after the break, we have the talk of Giancarlo. So let's make a break